In this video, we're going to talk about one of the additional properties of the Laplace transform that allows us to calculate transforms of functions without actually having to go back to the original definition. In today's video, we're going to talk about a sort of equivalent to the product rule for derivatives, but it's not going to be nearly as broadly applicable as the product rule was in Calculus 1. As it stands, even by the time the course is over, we will still be able to calculate the transform of a very limited collection of products of functions, and we will be able to transform basically no quotients of functions. It's so much more difficult here than it was in Calculus 1 that we don't really have a general product rule or quotient rule for Laplace transforms, but this is basically as close as we're going to get. Now, what if you want to find the Laplace transform not of f of t, but of the product of f of t and an exponential function e to the power a times t? What you can do is you can take the Laplace transform of the original function f of t and you can shift it horizontally. Wherever there was an s, you can replace that s by s minus a, where a is the same number that you're seeing in the exponential function in your product. Now, anytime we give a statement about the Laplace transform, a second statement is implied about the inverse Laplace transform. Note that this implies that if you take the inverse Laplace transform of a shifted function, then the result will be an exponential times the original function f of t. So we're going to use both of these results today to find the Laplace transform of a product exponential times function, and also to find the inverse Laplace transform of a horizontally shifted function. So first, let's practice using this result in the forward direction. And let's find the Laplace transform of t cubed multiplied by e to the negative 2 times t. So the first thing that I'm going to do is I'm going to find the Laplace transform of the function t cubed, which is being multiplied by this exponential. And for that, I can just use the table of Laplace transforms given in theorem 7.1.1. That theorem says if you're taking the Laplace transform of t to the power 3, that's equal to 3 factorial divided by s to the power 3 plus 1. So 6 divided by s to the 4th power. But this is not the Laplace transform that we want. The Laplace transform that we want is the transform of the exponential e to the negative 2 times t multiplied by t cubed. So in this case, I have an a value which is equal to minus 2, and so I need to replace all the s's with s plus s take away negative 2. That is s plus 2. So in the original Laplace transform, instead of having s to the power 4, I'm going to put in s plus 2 to the power 4. This is the Laplace transform of the given product exponential times t to the 3rd power. I'm kind of fond of the textbook's notation for this phenomenon. What they have written here is that if you want the Laplace transform of e to the negative 2t times t cubed, you can take the Laplace transform of t cubed and then replace, and this is what they write, replace s with s plus 2. And I'm rather fond of this notation. I think this is a good shorthand for what you're doing. So we would have 6 divided by s to the 4th power, and then we would write s replaced with s plus 2, and so that would give us 6 divided by s plus 2 to the 4th power. Nothing different, but I think that this notation is really nice and compact and a good way to keep track of what's going on. We can also use that theorem in reverse. And so let's go ahead and let's find the inverse Laplace transform of 2s plus 7 over s minus 4 quantity squared. Now, when faced with a rational expression, my instinct is to start by doing a partial fraction decomposition. And when you have a linear factor like s minus 4, which is repeated, which has a multiplicity of 2, you need to break the function down into two terms, one with an s minus 4 to the first power, one with an s minus 4 to the second power. Since the denominator is basically linear, we can guess a constant for the numerator. So I'll guess numerators of the form a and b. And now if we clear the fractions, multiplying through by the least common denominator, we get 2s plus 7 is equal to a times one copy of s minus 4 plus b. And therefore 2s plus 7 is equal to as minus 4a plus b. Now if I look at the s terms imply that a is equal to 2. You can get that directly. And if I look at the constant terms, then I get that 7 is equal to negative 4a plus b. Well, now I know that a is 2, so if I plug that in, I get 15 equals b. And therefore, what expression am I trying to find the inverse of? I'm trying to find the inverse transform of 2 divided by s minus 4 plus 15 divided by s minus 4 squared. Now, if you look at the table closely, you won't be able to find any particular entry which exactly matches what we have here. But what I'm going to notice about this expression is that this is the same thing as 2 over s plus 15 over s squared, where s has been replaced by s minus 4. So what I'm going to do is I'm going to find the inverse transform of the unshifted function, and I'm going to multiply the result by the exponential corresponding to a constant multiple of that 4. Now, using the table, the inverse transform of the unshifted function is equal to just 2 and then plus 15 multiplied by t. So if I take that and multiply the result by our e to the 4t, this function will be the inverse Laplace transform of the expression that we were given in this exercise. So to sum up, we broke this expression down using partial fraction decomposition into a sum of simpler functions. We recognized that our simple functions were horizontal shifts of entries in our table. So we took the inverse transform of the unshifted function, and then we multiplied the result by the corresponding exponential. It was shifted by 4, so we multiplied it by e to the 4t. Let's practice using this rule again in a slightly less straightforward manner. Let's find the inverse Laplace transform of 1 divided by s squared plus 4s plus 6. Now the thing about this denominator is that it doesn't factor. So this expression cannot be broken down any more than it already is using partial fraction decomposition. Now when the denominator does not factor, but when the denominator is still too complicated to represent any of the entries in our inverse transform table, the idea is to complete the square. So I'm going to take 1 over s squared plus 4s plus 6, and I'm going to rewrite it with the square completed. If I take half of 4, that's equal to 2. So I get s plus 2 quantity squared. Then take away 2 squared, and here's our 6 from the original expression. Now actually, to make things more interesting, I want to do an emergency override of this problem. I'm actually going to go ahead and change this 1 in the numerator to an s, just to show you something else that's important to keep in mind. So now I'm going to try and find the inverse Laplace transform of s divided by s plus 2 quantity squared plus 2. And in my table, I have an entry which is similar to this one in format, which is the inverse of s over s squared plus number squared is equal to cosine of number times t. Now it kind of seems like the expression that I have been given is a shift of s over s squared plus 2, where s has been replaced by the quantity s plus 2. But that's actually incorrect. If I replaced all the s's in this expression with s plus 2's, then the s plus 2 in the numerator would also get shifted, which doesn't currently match what I have. I currently have just an s and not an s plus 2. So to fix that, I'm going to make a quick adjustment. I'm going to take that s and then I'm going to add a 2 to it. But the price that I need to pay when I add a 2 is I need to subtract a 2 minus 2 over the same denominator. That way this is equal to what I started with. So now I can take the inverse Laplace transform of these two functions. So now that I've rewritten the first expression so that it's truly equal to a shift in one of the entries in my table, I ended up with a second term which is a shift of another one of the entries in the table, namely the entry concerned with sign. If I take the inverse of number divided by s squared plus number squared, the result of that is sine of number times t. So my function is equal to e to the negative 2t multiplied by the inverse Laplace transform of the unshifted function, s divided by s squared plus 2 minus 2 divided by s squared plus 2. Now all I have to do is use the entries in the table to invert these two functions correctly. Now 2 is the same thing as square root 2 quantity squared, which means that in my second fraction I cannot have 2, I need to have a root 2 in the numerator. So I'll put a root 2 in the numerator at the cost of moving the second root 2 aside. And finally, I get e to the negative 2t times the inverse Laplace transform of the first function, cosine of root 2 times t, minus the square root of 2 times the inverse Laplace transform of the second fraction, which is sine of root 2 times t. So now that we've done a few abstract examples of transforms and inverse Laplace transforms that use the given theorem, let's go ahead and apply the theorem in the context of an actual initial value problem. For example, in this initial value problem, if I start by applying the Laplace transform to both sides, then y double prime will become s squared multiplied by capital S minus s times y of 0 minus y prime of 0. Then the negative 6 times y prime term will become negative 6 times the quantity s times f minus y of 0. And then the plus 9y will become plus 9 times the Laplace transform of y. On the right-hand side, we have the Laplace transform of a product, exponential, multiplied by t squared. And the theorem says that you can take the Laplace transform of t squared and simply replace s with s minus 3 in the result. Now the table says that the Laplace transform of t squared is equal to 2 divided by s cubed. So if I replace the s with s minus 3 in that result, then I get 2 divided by s minus 3 quantity cubed. So now if I use our initial conditions, we find that we have s squared times f minus 2s minus 17 minus 6s times f minus 6 times negative y naught, which is plus 12, plus 9 times f is equal to 2 divided by s minus 3 quantity cubed. So s squared minus 6s plus 9 quantity times f is equal to 2 divided by s minus 3 quantity squared. Add 2s to both sides and then move that 5 over as well. The 5 that we get from combining negative 17 and positive 12. So our function, using the fact that s squared minus 6x plus 9 is the same thing as s minus 3 quantity squared, our function capital F is equivalent to 2 divided by s minus 3 to the 5th power plus 2s plus 5 divided by s minus 3 to the 2nd power. Now, as usual, when I'm doing inverse Laplace transforms, I'm going to take a close look at these rational expressions to see if there are any that can be broken down into a sum of simpler fractions using partial fraction decomposition. And the one that draws my attention is this guy here in the back. We have a linear factor in the denominator, s minus 3 quantity squared, but we have something which is of the same degree in the numerator. So that's an opportunity to use partial decomposition to split this into a single number over s minus 3 plus a single number over s minus 3 quantity squared. So let me go ahead and clear the fractions. We get 2s plus 5 is equal to as minus 3a plus b. So the s terms imply that a is equal to 2, which implies that 5 is equal to negative 6 plus b, using the fact that a is 2. So b is equal to 11. And replacing a with 2 and b with 11 in my partial fraction decomposition, I now know that my function capital F is equal to 2 over s minus 3 plus 11 over s minus 3 squared plus the 2 over s minus 3 to the 5th power, which was already completely decomposed. Now I'm going to note that what I have here is the same thing as 2 over s plus 11 over s squared plus 2 over s to the 5th power, where all the s's have been replaced with s minus 3's. So if I can find the inverse Laplace transform of this expression in yellow, then I can multiply the result by e to the positive 3t and get my solution. The inverse Laplace transform of 2 over s is equal to just the number 2. The inverse Laplace transform of 11 times 1 over s squared is equal to 11 times t. But in order to inverse 2 over s to the 5th power, I'm going to need to do a little bit of adjustment. The table says that the inverse Laplace transform of s to the 5th power with a 4 factorial, a 24 in the numerator, that would be equal to t to the 4th power. But I don't have a 24 in the numerator, I just have a 2. So what I'm going to do is I'm going to multiply the extra factor of 12 that I need at the cost of dividing by that same 12. So now I have plus 1/12 t to the 4th power, and if I multiply that by e to the 3t, then that is our y value. That is the solution to the initial value problem. Now this is a situation where I think that Laplace transform has a truly distinct advantage over the method of undetermined coefficients to solve this problem. It turns out that in order to use method of undetermined coefficients to find a particular solution, you would have to guess some monstrosity of the form t to the 4th power, at to the 4th power, plus bt cubed plus ct squared, quantity times e to the 3t in order to find the correct particular solution. And you can imagine how much of an irritation it would be to have to calculate y prime and y double prime using the product rule and then plug all of that into the ODE and find the values of these constants. So I think method of undetermined coefficients would be absolutely miserable here. And this is a situation where I think Laplace transform is distinctly advantageous and the better method to solve this initial value problem. That concludes today's material. Today we introduced a theorem that helps us to find the Laplace transform of an exponential multiplied by another function. But in reality, that theorem is more useful in the other direction to help us to find the inverse Laplace transform of functions which are shifts, horizontal shifts, of one of the entries in our inverse Laplace transform table.